Hello and welcome to today's lecture on synthesis for low power, a new VLSI design paradigm for DSM. DSM stands for deep submicron technology. As you know, we are now in the era of deep submicron technology. So, earlier low power design was not that much important, but as we are going towards deep submicron technology, it is becoming increasingly important. So, in this lecture, I shall cover these topics. Here is the outline. First, why low power? Why low power has become so important in the design of VLSI circuits. Then we shall consider sources of power dissipation. Whenever you want to design for low power or say you go for synthesis for low power, you have to know what really you have to do. That means you have to know your enemy. To know the enemy, you have to know the sources of power dissipation, and as we shall see, there are two basic sources. One is known as dynamic power dissipation, another is static power dissipation. So, we shall discuss in detail about these two. Then we shall identify degrees of freedom, that means by which we can really you can reduce the power dissipation. Then we shall discuss some low power techniques, particularly supply voltage scaling techniques, minimizing switching capacitance, and lastly leakage power reduction techniques. First, let us focus on why low power. Until recently, performance has been considered the most important parameter in the synthesis of VLSI circuits. For example, whenever a new processor is introduced, people will say this is the performance in megaflops or number of million instructions per second it can do. So, in terms of MIPS or megaflops, the performance is stated, and that was considered to be the most important parameter. And implementation involved area time trade off. That means having larger area, you can have more better performance, and it can be explained in this way. Say power consumption is equal to K into A and F, where K is a constant which is roughly equal to 0.063 watts per centimeter square megahertz, and A is the area in centimeter square, and F is the frequency in megahertz. And in those days, power consumption were of secondary concern. People were not bothered about power consumption. Now, let us see why power consumption has become so important. If you look at the contemporary high performance processors, you will find that these are consuming heavy power. For example, here I have considered few representative processors, say Altair-Spark, Intel Pentium, and Alpha 610-21064. These are essentially the RISC processors developed by Alpha DEC, and these are known as DEC Alpha chips, which actually were developed for high performance and were used in making servers and workstations. If you see that clock rate has increased starting with 167 megahertz to 1000 megahertz. So, most of the processors are now operating in the range of gigahertz, and here it shows the advancement of technology. That means the size is gradually shrinking starting with 0.45 micron to 0.25 micron. As you know, we are now in the era of 60 nanometer or 45 nanometer. So, this is little older picture, and as you keep on decreasing the size, the supply voltage is also reduced to reduce power dissipation, and in spite of that, as you can see, the peak power dissipation has increased from 30 to maybe 100 watts. So, most of the processors which are being used nowadays, high performance processors consume 100 watts. So, to dissipate 100 watts, you have to develop suitable cooling and packaging technique. When I joined IIT Kharagpur, we had a cyber computer, Russian made cyber computer, and the processor was cooled by using chilled water. So, we had to set up a chilling plant, then the chilled water has to be circulated around the CPU, and so you can think about the cost of cooling. So, cost of cooling was enormous. So whenever a chip is dissipating 100 watts, obviously you have to develop very sophisticated packaging and cooling technique. For example, if you open up a laptop or a PC, you will find on top of the processor there is a big heatsink and there is a fan built in as part of the heatsink. So that is what is required. So how you can really reduce the cost of packaging and cooling? The only way to do it is to develop suitable low power design methodology so that the power dissipation is reduced. This is one reason why low power is so important. Second, you can see here how the power dissipation of Intel processors has increased over the years. You can see it has reached 100 watts, close to 100 watts, in spite of the fact we have gone from 1.5 micron to 0.13 micron for Pentium processors. Now, of course, the latest processors have been introduced with technology of smaller dimensions. However, the lead processor power increases every generation. As you go from one generation to next generation, the number of transistors per chip is increasing, and as a consequence power dissipation is increasing. So compactions provide high performance at lower power. In spite of that, you are reducing the dimension, so you are able to put more and more transistors. So performance is improving because of more number of transistors. But that because of the astounding increase in the number of transistors, the power dissipation is increasingly getting higher and higher. Look at the power density. Power density is a parameter which is power per unit area within the chip. You can see here how the power density is increasing, particularly in this region. You can see it has reached the temperature of hot plate. So there was a cartoon that there is a roadside cafeteria where somebody is frying eggs by putting it on the processor, because processor temperature has increased the temperature of a hot plate. So you can use it for frying eggs. So that kind of scenario is emerging, and if it is not controlled, it will very soon reach the power density of nuclear reactor, then the rocket nozzle. You can see whenever the power density is in this area, obviously the chip will not be very, it will be very hot, and failure rate will be very high. So you have to develop suitable techniques, low power design techniques, so that the power density is reduced. Then another compelling reason for considering low power is the emergence of portable equipments. Nowadays everybody is carrying cell phones, laptops, pump tops, all are battery operated. So in case of battery operated devices, battery life is of primary concern. That means whenever you are using a laptop, you want it to last for the whole day. But unfortunately, even today, if you charge a battery, laptop will sustain maybe for 3 to 4 hours, not longer than that. And in such cases, the battery technology is very important, but unfortunately the battery technology has not kept up with the energy requirement of the portable equipment. So new technologies are emerging for batteries, but battery technology is not advancing at the same rate as the processor technology. So the gap is widening. That means maybe it is increasing this way and battery technology is increasing this way. So gap is widening with time. And in case of portable equipment, commercial success of these products depend on the weight, cost and battery life. That means whenever you go for buying a cell phone, first you will say how small it is, whether it is weight is less than 100 milligram or not, and how long the battery will last. So is true for pump tops, laptops and other portable equipment. So you can see the viability of a product, sellability of a product depend on the battery life, and this in turn depends on the power consumption of the processors you are using inside the system. So low power design methodology is important to make them commercially viable, particularly portable equipments. Let us now come to another very important reason, that is your reliability. Reliability has been found to be closely related to the temperature rise within the chip. And it has been found that every 10-degree rise in temperature roughly doubles the failure rate. That means if the temperature rise from say 40 degree to 50 degree, failure rate doubles. So the chip will fail. And the reason for that can be is very clear from this from this onset temperature of various failure mechanism. So within the chip, various failures can take place like silicon interconnect fatigue, failures due to silicon interconnect fatigue, failure due to package related failure. I mean, chip may fail because of package related failure, electrical parameter shift, electromigration diffusion, junction diffusion, gate dielectric, thermal runaway. So you can see these are the typical temperature in degree centigrade above the normal operating temperature. So that means if the temperature is 100 degree above the ambient, then you can see the failure rate will be some of these two failure mechanisms will be active, and as a result the chip will fail. So you can see reliability is closely related to the rise in temperature, which in turn is closely related to the power dissipation of the chip. So you have to use low power design techniques so that the power dissipation is small. Lastly, according to an estimate of the US Environmental Protection Agency, 80% of the power consumption by office equipment are due to computing equipment. That means the computers and various other equipment, those peripherals and other things, they consume 90% of the power consumption. And ironically, most of them are unused. It was the scenario that the 100 computers are on, but a small percentage are really in use. Computers are on, power is getting dissipated, they are not being used. And whenever the what you really do about the power dissipation, power is dissipated mostly in the form of heat. That means the computers, peripherals, they are dissipating power, and which is converted into heat. And what you are doing, you are turning on the AC, the air conditioner is taking the heat from the room, putting it outside, so environment is getting heated. Moreover, you are using toxic gases in air conditioners, so which is also polluting the environment. So to reduce the adverse effect on environment efforts such as EPA's Energy Star program leading to power management standard for desktops and laptops have emerged. Nowadays, whenever you don't use a computer for some time, what happens? It automatically shuts down. Some of the screen will become black, some of the subsystems within the computer will turn off, will switch to standby mode, low power mode. This is because of this particular this green PC, drive towards green PC and the standard which have been developed for this purpose. So you see, low power methodology has already been adopted in case of your laptops and other equipment. Even if you don't use some battery operated equipment for some time, it will automatically switch off the power hungry subsystems. So now I believe you are convinced that low power design is very important. Are you convinced? Okay. So now let us look at our enemy, the sources of power dissipation. As you know, CMOS has emerged as the technology of choice for low power applications and is likely to remain so in near future. So many other technologies are emerging. People are telling that gallium arsenide will be the technology of the future. People are telling that quantum computing will become popular in near future. People are telling that optical computing will become popular in the near future. But as of today, CMOS based VLSI circuits are the technology of choice of the computing equipment that you are using, and I believe it will remain so in the near future. So let us focus on CMOS based circuits and let us look at the power dissipation of CMOS circuits. And in CMOS circuits, the sources of power dissipation in CMOS circuits can be broadly divided into two types, dynamic power and static power. What is the difference between dynamic power and static power? Dynamic power is essentially when the circuit is in operation, circuit is in action, that means it is doing some processing. On the other hand, static power is when the circuit is in the standby mode. We have already seen that whenever that some circuits are not in use, it can be switched to standby mode. Unfortunately, even when the circuit is in standby mode, it consumes power, although it is much smaller than the active power. So, we shall look at the sources of power dissipation, both of dynamic power and the static power. The dynamic power can be broadly divided into three types: switching power, short circuit power and glitching power. And static power is due to reverse bias junction diode currents when the transistors are off, and due to subthreshold leakage current, as we shall see explained in detail. So, first let us focus on the dynamic power. This is the schematic diagram of a CMOS circuit. As you know, there is a pull up network made of PMOS transistors and there is a pull down network made of NMOS transistors, is not it? Now, for some input combination, output will become high. When the output is high, essentially from the supply voltage VDD, this capacitor, load capacitor is charged through the PMOS network, and whenever for some input combination, when the output is 0, that charge which was stored in the load capacitance will be dissipated through the NMOS network. That means while charging, power is dissipated in the PMOS network, and while discharging, when the output becomes 0, the discharging takes place through the PMOS network and power dissipation takes place through the PMOS network. And this is the dynamic power dissipation which takes place across the load. Actually, it is equal to alpha L. Alpha is the switching activity. For a particular input combination, transition does not occur for each clock. It depends on the input. For example, if it is a NAND gate, the output will become high only when all the inputs will become low only when all the inputs are 1, and it will become 0 when any one of the input is 0. So, that means the transition to 1 and transition to 0 does not occur at each clock. That is why there is a parameter called switching activity, which is dependent on the input function the circuit is realizing. The function the circuit is realizing and depends on the input combination that is being applied to the combinational circuit. And CL is the load capacitance, VDD is the supply voltage, and F is the frequency. So, this is the power dissipation, and actually half of it is dissipated while charging the capacitor and half of it is dissipated while discharging the capacitors. That means half of the power is stored in this capacitor after charging, and that stored energy is dissipated while discharging when the output becomes 0. And this part is actually due to power dissipation within the internal nodes. Whenever you are realizing a very complex CMOS circuit, apart from the output node, there are many internal nodes where there are capacitances. So, though they will be also charged and discharged, leading to power dissipation. So, this part corresponds to the power dissipation in internal nodes. So, you see this is the switching power dissipation, and as you can see, it is proportional to the load capacitance, it is proportional to VDD squares, and it is proportional to the operating frequency. And last but not the least, it also depends on the switching activity. So, you remember these parameters. So, you can see if you want to reduce dynamic power, what you have to do? You have to reduce CL, you have to reduce alpha L, you have to reduce VDD. And this is this is essentially the derivation of that equation. I am skipping it, not going into the details. You can derive it, that the power dissipation will be equal to CL VDD square F, and of course here we have not taken into consideration the switching activity. Here it has been assumed that the power dissipation occurs, transition occurs in each clock whenever you take into consideration the switching activity, you have to multiply alpha L with it. And second type of power dissipation, dynamic power dissipation, is known as short circuit power dissipation. As you know, in case of CMOS circuit, when the output is 1, then the PMOS network path is on open, but the NMOS network path is closed. On the other hand, when the output is 0, the NMOS network path is open, PMOS network path is closed. In other words, there is no direct path from supply to ground. Say this is a simple inverter, that means when the input is 1, this is on, when the input is 0, this is on. But normally for low and high inputs, there is no direct path from the supply voltage to ground. So, in other words, there should not be any short circuit path, short circuit current passing through the transistors. But unfortunately, when the input changes slowly like this, or I mean from 0 to 1, or low to high, or from high to low, you can see there is a region in between where both the transistors are on. That means when the input voltage is greater than the threshold voltage of the NMOS transistor and less than the threshold less than VDD minus threshold voltage of the PMOS transistors, for that part of the input both the transistors will be on, and as a consequence there is a short circuit path from supply to ground, and this is known as short circuit power dissipation. And the short circuit current that will pass can be derived as 1 by 12 into K tau F by VDD into VDD minus VT. VT is the threshold voltage to the power cube to the power 3. So, you see here also it depends on the supply voltage VDD, it depends on the frequency, and tau is the rise time and fall time. So, tau is the transition time and K is a constant. So, here also there is a strong dependence on supply voltage, there is strong dependence on frequency, and there is dependence on the rise time and fall time. And this also can be derived by the short circuit current, power current can be found out. This is the derivation, and I am not going into the details of it. You can later on look into it more details. So, the short circuit current power dissipation will be equal to, as you can see, beta by 12 VDD minus 2 VT cube tau into F. Tau is the rise time and fall time, and F is the frequency. We have assumed here both the rise times and fall times are same for the sake of simplicity. There is another dynamic power dissipation which is known as glitching power. The glitching power is due to non-zero delay of the gates. If the gates do not have any delay, if you assume that gates do not have any delay, then there will be no glitching power. But unfortunately, all the gates will have some delay, and the glitching power can be explained with the help of this simple example, simple circuit comprising two NOR gates. Here you can see for these two input combinations 101 and 000, output is supposed to be 0 for both the inputs, but as you change the input from 101 to 000 for a brief duration, the output becomes high. I mean, that is one gate delay. For one gate delay duration, output will become high because of no delay of this gate. That means you can see this output is 0 when the input is 101. This output is what? Output will become 0, as you can see here, and this 0 will continue after the transition is occurring to 000 for one gate delay, and as a consequence here the input will be, this input will be 0 and this input will be 0. So, when both of them are 0, what will happen at the output? Output will become 1, and that 1 will remain for one gate delay duration, and this is known as glitching power. And as you know, whenever a capacitor is charged and discharged, there will be power dissipation. So, here also this particular gate has some capacitance at the output, and that will be charged here and it will be discharged here, and as a result there will be some power dissipation. And in case of CMOS circuits, the glitching power dissipation is not very small, not very insignificant. In fact, it has been found to be quite large, because you will be realizing multi-input, multi-level circuits. A circuit will have multiple levels. So, within the circuit there will be lots of, if you change the input combination from one input to another input combination, or one input vector to another input vector, before the output stabilizes, internally there will be lots of transitions, and that will lead to power dissipation, which is known as glitching power. Then coming to the leakage power dissipation, that standby power, that static power is essentially known as leakage power. That means when the circuit is in standby mode, that means the inputs are not changing, clocks are not changing, so circuit is in standby mode, but the circuit is connected to the supply voltage, and as a result it will lead to some power dissipation, and it is primarily due to leakage current. So, this is a typical MOS transistors. I hope you are familiar with the structure of a MOS transistor. So, here is, these are the source, and this is the source, and this is the drain region, this is the drain, this is the source, and this is the gate region. And you can see there are different types of currents: I1, I2, I3, I4, I5, I6, I7, and these are these currents. I1 is the reverse bias PN junction diode leakage current, I2 is the band to band tunneling current, I3 is the subthreshold leakage current, I4 is the gate oxide tunneling current, I5 is the gate current due to hot carrier injection, and I6 is the channel punch through current, and I7 is the gate induced drain leakage current. Let me very briefly tell about these various leakage currents. You can see here, this is the typical CMOS inverter. Here you can see this is the NMOS transistor, and this is the PMOS transistor. This is the N well, and this is the P type substrate, and you can see here this is P, this is N, this is N, this is P. So, you can consider as a diode, this is N, N plus, and this is P. Here also this is P plus, and this is N. So, it forms a diode like this. So, within the geometry of the device you have this kind of diodes, P N, N P, N P, like that, and these diodes are reverse biased. As you know, when a diode is reverse biased, it will have some reverse bias current, and that reverse bias current is the equation for reverse bias current is this: AJS into to the power, e to the power q Vd by nkt minus 1, and Js is the reverse bias reverse saturation current density, Vd is the diode voltage, that voltage across the diode, N is the emission coefficient of the diode, and which is usually considered to be 1, and Q is the charge of electron, K is the Boltzmann constant, and T is the temperature. So, here you see this leakage current is dependent on temperature, is dependent on the area, active area of the device, and also the reverse saturation current density. And this current has been found, there are many transistors within a chip. So, you have to take into consideration all the transistors. You have several million or a billion transistors within a chip nowadays. So, you have to sum up all the currents passing through it. So, if you have 1 million transistors, then this current is roughly equal to 0.1 microwatt. So, you can see when it is 1 billion, then it will become 1000 times of that, then you cannot really ignore any longer. When the number of transistors is small, it can be ignored, but when the number of transistors within a chip is very large, then the current due to this reverse bias diodes will be quite large. Then the second type of current is known as band to band tunneling current. That occurs because, as the size of the transistors are shrinking, although the voltage across the gate and substrate or drain to source is very small, 1.8 volt or 1 volt nowadays, but the size is very small, say 60 nanometer. So, that creates a tremendous field, electric field, and because of that this band to band tunneling occurs. High electric field across the reverse bias pH junction causes significant current known as BTBT current, band to band tunneling. Here you can see the electrons move from the valency band to the conduction band, leading to current across the PN junction. There we have seen that the current occurs. This is in the I2 is actually taking place during this junction. So this is because of the band to band tunneling. So the I1 is due to reverse bias diode and I2 is due to band to band tunneling. And this is the expression for the band to band tunneling current. I am not going into the details. You can you require lots of knowledge of the semiconductor physics to understand these equations, but these currents are not very significant, not very insignificant. Then coming to the another very important leakage current source, that is your subthreshold leakage current. Normally we know if you apply voltage to the gate and if the voltage is less than the threshold voltage, we assume that the transistor is off, no current is passing through the channel, but unfortunately in reality that is not true. Even when the voltage is less than the threshold voltage, current is not very small, and whenever the voltage is close to the threshold voltage but less than it, that current is quite high, and that is known as subthreshold leakage current. And this is the expression for subthreshold leakage current, and this current increases drastically with temperature. As you can see, it has strong dependence on the temperature, and it also increases at threshold voltage is scaled down along with the power supply voltage for better performance. And actually the subthreshold leakage current increases exponentially with reduction of threshold voltage. When the threshold voltage is high, subthreshold leakage current is small, but as you reduce the threshold voltage, which you have to do because of device size scaling, later on we shall come to that, and as you reduce the threshold voltage, the subthreshold leakage current increases significantly. And the subthreshold leakage current is dependent on many phenomena, many factors and phenomenon. One is drain induced barrier lowering, body effect, narrow width effect, effect of channel length, and VTH roll off, and effect of temperature. And because of this, the subthreshold leakage current is very important, and in fact it is one of the dominant source of leakage current in present day VLSI circuits. Now if you compare make a relative comparison of the different types of currents, you can see switching power contributes 80 to 90%, leakage power contributes 10 to 30%, short circuit power contributes 0 to 5%. Question is at what technology? This is the case for 180 nanometer technology. As the device size is sinking, the scenario is different, as you can see here. So the active power is increasing, but rate of increase is not very high. But leakage current, you can see, which is the standby current or static current, that is increasing at a very high rate, larger rate. And you can see this is 0.18 micron, there is maybe almost 2 order of magnitude difference here, but whenever we go to 90 nanometer, it will become same. That means the leakage current will become same as the dynamic current, that means the active power dissipation or dynamic current, which is due to those charging and discharging of capacitors and other sources. So if you look at this diagram, it will be very clear. You can see for 0.25 micron, this static current is insignificant, you can ignore. 0.18 micron, yes, it is visible, but whenever we go to 70 nanometer, leakage current is more than the active current. So you see, as the technology is advancing, as we are going to deep submicron technology, our main concern is leakage current, and that's why most of the research is focused on lowering the leakage current, how to reduce the leakage current. Now, we have already discussed the various sources of power dissipation. Now, let us see the degrees of freedom. Degrees of freedom means how we can really control the power dissipation. Number one is supply voltage. We have seen that power dissipation, all sources of power dissipation is dependent on the supply voltage. In one case, in case of leakage current is proportional to VDD. In case of switching power dissipation, it is proportional to VDD square. In case of short circuit current, we have seen it is proportional to VDD minus VT cube. So, always there is a strong dependence on supply voltage. That is why the supply voltage has the most dominant effect on the power dissipation because of quadratic relationship in case of dynamic power dissipation. Then comes the physical capacitance. We have seen the dynamic power dissipation is proportional to the capacitance, switching capacitance, physical capacitance, and also it is proportional to the switching activity. That means whenever we consider, whenever we say optimizing power consumption, that will invariably involve reducing one of these parameters. Either you will try to reduce power dissipation by scaling down the supply voltage, or by minimizing the capacitance, or minimizing the switching activity. And usually when product of capacitance and switching activity is known as switched capacitance. You will try to minimize the switch capacitance. And also as I told, in present day context, leakage power is becoming very important. So, you have to give special emphasis to reduce the leakage power dissipation. Now, low power design methodologies are to be applied throughout the design process from system level to layout level. As you know, whenever you go for a VLSI design, you have to go through a design hierarchy. You will start with the system specification. From that, you will come up with a system level design. Then you will start with a behavioral description. From that, you will get high level, you will perform high level synthesis or RTL level synthesis. From the structural RTL level description, you will go for logic synthesis, and from logic circuit, you will go for logic level netlist, you will go for layout synthesis, finally to get a layout. So, these are, you have to go through a number of steps, and we have to apply low power design methodology in each and every level of design hierarchy, so that the power dissipation is minimized. And the impact of using low power design methodology at higher levels is more. For example, here if you use low power design methodology in behavioral or algorithmic level, there is a scope for reducing the power dissipation by 90 to 99%. If you use it in the architectural level, there is scope for reducing the power dissipation 10 to 90%. In the logic level, there is scope for reducing roughly 15%. In circuit level synthesis, if you use low power design technique, you can reduce by 30%. And the physical design, that means routing, placement, and so on, you can reduce by 20%. So, you see, if you start at the higher level, you will be able to reduce more than if you do it at lower level. Now, I shall discuss several design techniques that can be used for lowering the power dissipation. As I told, first one is voltage scaling. And so, supply voltage scaling is one of the most dominant technique used for reducing the power dissipation. So, there are several techniques by using supply voltage scaling. Number one is device feature size scaling. Second one is architectural level approaches using pipelining and parallelism. Third is by using voltage scaling using high level transformations. Third is by using dynamic voltage scale. So, let us discuss briefly some of these approaches. We have seen as you reduce the supply voltage, the energy drawn from the battery reduces in this manner. So, you will be always tempted to operate at a very low voltage. That means, if the circuit is operating at 5 volt, you will try to reduce operate it at 1 volt. Obviously, the power dissipation will decrease because there is a dependence, square law dependency on supply voltage is there. But there is one problem, there is a catch. Catch lies in this: as you decrease the supply voltage, then the delay of the circuit increases. So, that means, as you reduce the supply voltage, the delay of the circuit will increase. So, that means, by reducing the supply voltage, you can definitely reduce the power dissipation, but your performance degrades. That is not acceptable to us. So, we have to develop technique such that we can reduce the supply voltage, but without compromise in performance. That is the challenge. How it can be done? First technique that is used is known as device feature size scaling. Thanks to Moore's law, this device feature size scaling is continuing for the last 3 decades. You can see here, in the year 1985, the feature size, that means the minimum dimension of the transistors, was 2.5 micron, and in 2003 it is 0.18 micron. As you go from one generation of technology to the next generation of technology, you reduce the feature size. What do you really mean? By that we mean, this is a typical MOS transistor, structural diagram of a MOS transistor. By feature size scaling, we mean we reduce the size of the oxide thickness. If it was T-ox, you divide by S, by a factor S, which is greater than 1, maybe 1.3, or you multiply it by 0.7. It is like this. You reduce the doping concentration in these regions, in source and drain regions. You increase the doping concentration. You reduce the length. Length is the channel length, by a factor S. You reduce the penetration of the diffusion regions, both at the source and drain, by a factor S. You reduce the width of the transistor by a factor S, and also the substrate doping you increase by a factor S. So, this is known as device feature size scaling. As you do it, you can adopt 2 basic approaches. One is known as constant field scaling, another is known as constant voltage scaling. So, whenever you do constant field scaling, which I have already explained, these are the benefits. That means, capacitance reduces by a factor S, current decreases by a factor S, S is a scaling factor, power dissipation reduces by a factor S square, power density remains same, that's good thing. Delay decreases by a factor S, that means the circuit becomes faster. You have reduced the supply voltage by a factor S, you have also reduced the threshold voltage by a factor S, and as a consequence the delay has reduced by a factor S, and energy that is drawn from the battery by the circuit reduces by a factor of S cube. So, you see, device feature size scaling, so far we have enjoyed the device feature size scaling that has taken place over the years in the last 2-3 decades, and we are able to make faster and faster processors operating from, in the early years, in the 70s, the circuits used to operate, a microprocessor used to operate with few megahertz. Now, most of the microprocessors are operating at the speed of few gigahertz. The reason for that is this scaling, this device size scaling. So, this is very good, but unfortunately, you cannot always reduce the supply voltage, and also you cannot always reduce the threshold voltage, and that leads to what is known as constant voltage scaling. So, whenever you do constant voltage scaling, you do the feature size scaling except scaling the supply voltage and threshold voltage, and the effect is you can see power dissipation no longer decreases, but increases by a factor of s, and power density increases by a factor of s cube. That means, over the same area the power dissipation is becoming s cube times, which is definitely not very good for low power design. And delay is, of course, delay is decreasing by a factor of s square instead of decreasing by a factor of s in the previous case. Here it was decreasing by a factor of s, but here is decreasing by a factor of s square, because you have kept the supply same, supply voltage same. As you reduce the supply voltage, delay increases. So, this shows I mean how it occurs. Okay, so device feature size scaling is one important technique, and which has been adopted over the years, and we are actually enjoying the fruits of this device feature size scaling. Second thing, second technique that I shall discuss is architectural level approaches. One is parallelism. Parallelism means duplicating some circuit. Normally, you know, say suppose you have to, your work volume has increased. What you normally do? You increase the manpower. So, by increasing the manpower, your performance is increased. So, similarly, what you can do within the processor, you can keep on duplicating the circuit, say more than one processing element. For example, nowadays multi-core has become very popular, using 2 processors, 4 processor, 8 processor, and so on. So, by increasing, normally we think that by increasing parallelism the power dissipation increases, because the circuit is, hardware is duplicated, but you can use it in a different way. You can if whenever you use it for increasing the performance, then the power dissipation increases. But if we keep the performance same, then power dissipation can be reduced. I shall explain how it can be done. What happens, the basic idea is this: here what we are doing, we are trading area for power. We are increasing the area, but power dissipation is reduced. How? The reason for that is, when you are increasing the area, the power dissipation increases linearly, but when the power dissipation increases linearly, but what you can do, if we want to have the same performance, we can reduce the supply voltage. The circuit can operate at a lower speed, and that will, and whenever you make the supply voltage half, power dissipation reduces by a factor of 4. So, by increasing the area, power dissipation increases by a factor of 2 if you double it, but by reducing the supply voltage, power dissipation reduces by a factor of 4. Overall, power dissipation becomes half. So, let us take an example that will make it clear. So, here you see, this is our reference circuit. Here is a 16-bit adder. You are applying 2 operands A and B through 2 latches to it, and to get 16-bit output. And this is the dynamic power dissipation. C reference is the overall capacitance of the circuit, V reference is the supply voltage, and F reference is the operating frequency. Now, you do the duplication, parallelism. So, here you see we have got 16-bit adder, 2 16-bit adders, and of course, you have to use a multiplexer to get the data at the same speed as it was done in the previous case. But this part of the circuit now can operate at half the frequency, because here you are getting the output at the rate of f. So, and you are doing multiplexing. So, this part of the circuit can operate at half the speed, and so you can reduce the supply voltage of these 2 circuits. So, as you do that, what happens, you see, the capacitance obviously becomes more than double, because you will require multiplexer, and this part is duplicated. So, the capacitance has now become 2.2 C reference, but the supply voltage is half, so it becomes V reference by 2, and operating frequency is now F reference by 2. So, if you multiply, it will become, with respect to your P reference, how much it will become? So, this factor will be 8, 2.2 by 8. 2.2 by 8 roughly 1/4. So, you can see the power with the keeping the same performance, the power dissipation has become 1/4. So, what we have done? We have traded area for power. The cheap area has doubled or 2.2 times, but power dissipation is reduced by a factor of about 4. So, this is how you can reduce power dissipation by using parallelism. Then there is another technique that is known as pipelining. I hope all of you know what is pipelining. What is pipelining? Pipelining is dividing a task into a number of subtasks, and each subtask is performed parallelly. That is your pipelining. For example, a processor, whenever it is executing an instruction, what it does? Instruction fetch, instruction decode, operand fetch, execution of instruction, write back of the result. These are the different steps. So, if you do everything in one go by using a hardware, that is your non-pipeline processing. But what you can do, you can divide each of the each steps of the instruction execution into a number of subtasks. So, you use a subsystem which will do only instruction fetch, another subsystem which will do only decoding of instruction, like that. Here also what you are doing, 16-bit addition is divided into two 8-bit additions. So, the 16-bit addition task of performing 16-bit addition has been divided into two subtasks performing two 8-bit additions. So, output of this addition is applied to the next stage to perform another 8-bit addition, and as a consequence this adder is now, delay of this adder will be half of the 16-bit adder. If you consider simple ripple carry adder, the number of stages will be half of the 16-bit adder. So, here you can apply half the voltage, here also you can apply half the voltage, but the area wise you can see only it will be equal to 1.15 C reference, I mean compared to our original area, and voltage now you can reduce by half because the circuit delay is half. So, to get the same performance operating at the same frequency, you can reduce the supply voltage by half and operating frequency is F. So, you can see compared to our reference power dissipation, it is 0.28 times. So, by using pipelining without much increase in area, we are able to reduce the power dissipation by a factor of about 4. It is 0.28 P reference. So, you can see pipelining in all the modern processors that you are using nowadays, Pentium or any other processor starting from 386, 386, 486 and Pentium, everywhere pipelining is used, and the basic concept used is same what I have told, dividing a task into a number of subtasks and carrying out those subtasks parallelly. Of course, there is scope for using pipelining and parallelism simultaneously, and whenever you do that, obviously the reduction will be more. So, it will be roughly close to 1/10 of our reference circuit. So, by using pipelining and parallelism both, here you can see this part is pipeline, this part is pipeline, then it has been duplicated, and you are using a multiplexer to multiplex the two parallel stages. So, each of the parallel stages are pipeline, and as a consequence power dissipation here, as you can see, it will be quite small, roughly 10% of the original circuit. Original circuit means original 16-bit adder. Now, we shall discuss about another very important technique that is used in that is being used in embedded systems and other processors, that is your dynamic voltage scaling. You know, the processing power requirement is not constant for all the applications. If you look at the CPU utilization of your desktop, you will find sometimes it is 10%, sometimes it is 20%, sometimes it is 30%, depending on the program you are executing. And depending on the applications, if it is a server, maybe the utilization will be 60 to 70 or 80%. If it is a desktop or laptop, then utilization is much less. In other words, workload is different at different instants of time. If you can predict the workload, what you can do, you can reduce the operating frequency to get the required workload of at a particular instant. And as you reduce the frequency, that means increasing the delay, there is scope for reducing the supply voltage. So, as you reducing the, so what you can do, depending on the workload, you can reduce the frequency as well as the supply voltage, and it will be done dynamically. So, for that purpose, only thing required is that processor has to operate at different frequencies. For example, power PC that can operate at different frequencies, and for the corresponding supply voltage required to operate at this frequency is given here. This is the supply voltage required to operate at 700 megahertz, and the relative power dissipation is 100. And whenever you reduce the frequency, say for a particular workload, the frequency of operation required is 200 megahertz, and that time the supply corresponding supply voltage required is 1.1. So, you can see that time the power consumption is roughly 12.7% of the earlier case. Only thing that you have to do is to design a processor which can operate at different supply voltage at different frequency, and it is not hard to do, it can be done. So, you can see for a typical processor, this is the operational range, and if you increase the voltage beyond 2.2 volt, it is destructive, and whenever if you reduce the supply voltage below say 0.75 volt, then it does not work. So, you can operate it over a range of maybe 0.75 to 2.2 volt, and correspondingly you can reduce the operating frequency and operating frequency and supply voltage. Then you can see the power dissipation can be lowered following this curve. So, you can see depending on the workload, you can vary the voltage and frequency, that is known as dynamic voltage scaling. Then the power dissipation, you can see it can be quite significant. If you only do frequency scaling, that means if you only reduce the frequency, keep the voltage constant, then of course it reduces, the power dissipation reduces linearly, because you know that dynamic power dissipation is proportional to F, CL VDD square F. But if you reduce both supply voltage and frequency, then VDD is reduced and frequency is also reduced, and as a consequence it follows this curve, this curve, and there is significant reduction in power. And this is the scheme you have to use for dynamic voltage scaling. Here you can see you have a variable voltage processor, that means the processor can operate at different supply voltage and different frequency. Only thing that you require, these are the different tasks getting generated from different sources and which are scheduled by the operating system to be executed by the processor. I hope you have attended some course on operating system, how the task scheduling is done, that you may be knowing. And here there is a workload monitor. This is also part of the processor, part of the operating system. It monitors what is the workload in the next time slot, and based on that it will generate a frequency, and corresponding to that frequency it will generate a variable supply voltage with the help of a DC to DC converter. So, using DC to DC converter, you will be generating different voltage. Using a circuit known as phase lock loop, you will be generating different frequency, and depending on the workload that is being predicted. And by that the power consumption of the processor can be significantly reduced. And this is the schematic diagram of a DC to DC converter. Here you can see there is a reference voltage, and there is a switch usually realized by MOSFET, and there is a low pass filter and pulse width modulator, and this is a comparator, this is a reference voltage to be generated, this one reference voltage to be generated. You can generate different voltage for a constant fixed voltage with the help of a DC to DC converter. So, that is the basic idea. So, we have discussed several techniques for voltage scaling. Some of them are static in nature, some of them are dynamic in nature, and by which you can reduce the power dissipation. Now, we shall consider some techniques by which the switched capacitance can be minimized. Switched capacitance means can be the area can be reduced as well as the switching activity can be reduced. Some of the techniques are listed here. One is hardware software trade off, second is bus encoding, third is using suitable number system, sign magnitude or 2's complement, fourth is by using some architectural technique, last is by using logic style. So, these are some of the techniques which can be used. I shall explain some of the techniques. What is hardware software trade off? Those who are designing some VLSI circuit, first step to be performed is known as hardware software co-design. What it really means? It means that which part you will realize by hardware, which part you will realize by software. It means that. That means some of the functionality can be realized either by hardware or by software. So, there is a trade off. If you want high performance, you have to use hardware to do it. So, hardware based approaches will provide you faster circuit, but it will be costlier, it will consume more power. Whenever the same functionality is realized by software with the help of a program, then it will be cheaper because hardware is not there. It will be slower. Obviously, it will not operate at a high speed and it will consume lesser power. I can give you a very simple example. Suppose analog to digital converter is required. You can buy a analog to digital converter from the market and use it in your circuit, or you can use an IP of analog to digital converter in your circuit. So, that is hardware based approach. Another alternative is you use a digital to analog converter and a comparator, then you write a program implementing successive approximation algorithm. So, that is a software based approach. There the digital to analog converter and the comparator will require much lesser area on the chip, but the program will be complex, but it will consume lesser power. So, in case of processor design, there are two basic approaches. One is known as superscalar approach, another is known as VLIW approach. Superscalar approach is, within a single CPU, you have multiple processing units. Your 386, 486 and Pentium all are superscalar architecture. So, whenever you have multiple processing elements like multiple adders, multiple ALUs, fixed point units, floating point units, instruction fetch unit within a single processor, what you have to do? You have to fetch a number of instructions, then with the help of a hardware known as dispatch unit, they will issue in parallel to the different functional units. So, a hardware is performing identifying parallelism in the instruction, then issuing different operations to the different functional units. That is done by hardware, and then you will require a in order retire unit which will actually produce the final output. So, conventional superscalar out of order CPUs use hardware to create and dispatch micro operations that can be executed in parallel. So, this is a hardware based approach. Another alternative is to use what is known as VLIW approach. VLIW stands for very large instruction word. Here you have that serial instructions of the Pentium. Then a compiler can identify parallelism in the instructions. Then it can create special instructions where multiple operations can be put together into a single instruction. For example, here you have got say 4 fields. 4 fields corresponds to 4 different functional units. So, this is floating point adder, this is integer adder, this is load, that means the instruction I mean load and store unit, and this is branch unit. So, your processor has got 4 functional units, and here that identification of the parallelism is done by compiler, by software, not by hardware. And whenever you do that, obviously you do not require power hungry hardware which does this identification of parallelism, instruction issue and all these things. And what is the impact of that? Let us see. So, I shall illustrate the explain this with the help of a case study. Transmeta is a name of a company who developed a processor known as Crusoe processor, and based on the VLIW architecture they developed a processor, and the instruction words are known as molecule. Molecule is a 64 or 128 bits long, and it can contain up to 4 RISC like instructions, as I have told. So, this is a 1 RISC like instruction, another RISC like instruction, another RISC like instruction. So, a single molecule can have 4 RISC like instruction, and all the atoms get executed in parallel because you have 4 different functional units. So, you are executing in parallel both in case of superscalar and VLIW, but difference is in one case you are taking the help of hardware, in the other case you are taking the help of software. There lies the difference. And let us see the basic scheme of this that transmitter's Crusoe processor. Here is your VLIW processor, and here at the outside those applications, operating system, BIOS, these are all Intel x86 instructions, I mean applications, which are essentially serial instructions, and those instructions are compiled with the help of a software known as core morphing software. So, this core morphing software is essentially performing the job of compilation, which converts the instruction level this is called instruction set architecture of Pentium to the instruction set architecture of VLIW engine. That means, code translation is done by this piece of software, and once it is done, the execution of the VLIW instructions consumes much less power. And you can see x86 code is compiled into VLIW code, and core morphing software insulates the x86 programs from the hardware engine's native instruction set. And let us see the impact. Same program, if you execute in a Pentium 3 processor, the temperature rises to 105 degree centigrade. Same program if you execute in Crusoe processor, the temperature rises to 48 degree centigrade. So, you see the difference. So, here it is much cooler compared to this. So, you are able to get the same performance, but with a much lesser power dissipation, much lower rise in temperature within the chip. So, this is the software hardware trade off approach. And in fact, nowadays you are using the that multi-core processors. They are also essentially you are using the concept of parallelism to reduce the power dissipation, as the power dissipation is the key motivation behind using multi-core processor architecture. Then coming to the bus encoding, you can see here nowadays SoC has become very popular. Silicon, I mean, you have got multiple processing elements on a single chip. And here what you do, from one sender chip you are sending another information to another receiver chip, and here this part may be off chip or within a chip from one processing element to another processing element. There are two alternatives. Now, through some bus you are sending some data from the sender chip to the receiver chip. Usually the capacitance of the off chip, whenever it goes off chip, is very high. It can be of the order of picofarad, compared to on chip capacitance is of the order of femtofarad. So 3 to 4 order of magnitude of capacitance. Now, whenever there are lot of transitions here, lots of power dissipation will take place. Whenever some data is sent from one chip to another chip, how it can be reduced? What you can do, before sending you can do encoding, and after encoding you send it to the other side. You do the encoding in such a way that the number of transitions that take place here is much lesser. That means switching activity you are reducing. And at the receiving end you do the decoding and get back the original data. And there are different types of codes. One is known as redundant code. That means the number of lines here is same as the number of lines here. That means n and m is same. Then non-redundant, where m is more than n, that means number of bit lines used here is more than the number of lines here. Or it can be memoryless, that means the decoder and encoder need not require any memory. It can be realized with the help of a combinational circuit. You do not require sequential circuit to realize it, or it may require memory. So, there are different types of coding technique that can be used. Basic idea or basic goals of coding is remove undesired correlation among the information bits that you are sending and introduce controlled correlation, and that can be done by several encoding techniques. One is known as one hot encoding. One hot encoding means only one bit will be 1, remaining bits will be 0. You do the encoding in such a way. So, whenever it transition occurs, there can be at most 2 bit changes whenever you change from one code to another code. So, this is one hot encoding. That means but here it is actually it is redundant encoding, because for n bits you require 2 to the power n lines. That means value of m will be 2 to the power n when it is n, because only one bit will be 1, remaining bits will be 0. So, it guarantees precisely 1 0 to 1 and 1 1 to 0 bit transition when different data bits are sent. Unfortunately, it is very good, but number of wires required increases exponentially, because it increases at the rate of 2 to the power n. So, it cannot be used for larger data size. Another encoding is known as gray coding. Gray coding you may be knowing. You see, this is the binary code and this is the corresponding gray code. You can see here, if you consider consecutive codes, they differ it only 1 bit. That means, if you send this after this, there will be only 1 bit change, or this bit after this, there will be only 1 bit change. So, if you send consecutive data, then there will be only 1 bit change, means the transitions will be much less. So, this is the basic idea of gray coding. Whenever you fetch instructions from memory through the instruction bus, as you know, your instructions are stored in consecutive memory locations normally, unless it is a branch or subroutine call or interrupt. Otherwise, instructions are fetched from consecutive memory locations. So, in such a case you can see number of bit transitions per instruction is reduced by using gray coding compared to binary coding for different benchmark circuits. This was tested with the help of a number of benchmark programs. You can see there is significant reduction in the bit transition per instruction, and you can see the bit transition is less, the power dissipation will be less. So, if it is instead of 2.57, if it is become 1.75, 1.71, roughly power dissipation will become half. But in case of data, there is no correlation. Data is random in nature. In such a case, this this gray coding will not give you any benefit, which is very clear from the same experiment performing on the data bus. So, you see, instead of decreasing, in some cases it increases, the number of bit transitions per instruction increases whenever you do on the data bus, but in the address bus is definitely it is beneficial. Another encoding technique is known as bus inverse encoding, where what you do, say you have sent some data now, next time you send either the original data or its complement. If the complement requires lesser number of transitions with respect to the previous data, then you send the complement, do not send the original data. Question is how the other side will come to know about it? You send one additional line informing that the original data or its complement being sent. So, it is a non-redundant encoding, but by doing that you can have a saving of about 25% when the value of n is 2, or when the value of n is equal to 32, you can have a saving of 11%. That means power dissipation can be reduced by 11%, and you can do something in between, say 32 bit bus can be divided into 4 groups of each of 8 bit, that will give you roughly 18.3% reduction in power dissipation, opposed to 11% reduction whenever you send the entire 32 bit along with one additional bit. But in case of whenever you do 4 grouping, you require 4 additional lines, that means 4 into 8, 32 plus 4. So, by using by additional redundancy, using more redundancy, you can have larger reduction in power dissipation. As it here the increase in power dissipation, I mean for different data bit, data size, say 2 to 32, how the number of bit transition is decreasing, that is being shown. Lastly, we have another encoding technique that is known as T0 encoding, zero transition encoding. Here what you are doing, say whenever you are sending consecutive addresses, if you know the original address, only thing that you have to inform the other side that these are consecutive. So, you keep on increasing by the same number of bit value, that means increase by the previous value by the stride means, for example, if it is a 32 bit bus, then you have to keep on adding 4. So, keep on adding 4 to get the next address. So, you need not really send the new address, you are keeping on sending the first address, and for 15 consecutive addresses you are sending the original address, only you are informing that keep on increasing the stride with the help of one additional line, that is your INCT. However, in case of say branch, subroutine call, jump or interrupt, you have to it will not be consecutive. So, in such a case you send the original address, original data, and increment bit is 0. So, in case you can see the number of transitions can be made almost 0, asymptotically 0. If you keep on fetching instructions from consecutive locations, the number of transitions becomes very 0, asymptotically it becomes very close to 0. In case of your gray coding, it becomes asymptotically 1, but here it becomes close to 0. Okay. These are the techniques used for bus encoding. Then I talked about the glitching power dissipation. How you can minimize glitching power? Glitching power can be minimized by balancing the circuit like this instead of realizing circuit in this manner. Suppose here you have to realize OR of A or B or C or D. You can realize the circuit this way. Same function can be realized by this manner, and in both the cases you require 3 OR gates. But the difference is, in this particular case glitching power dissipation will be more, because here the input, this input and this input are reaching at different time instant, this input and this input are reaching at different time instant. So, there will be glitching power dissipation in this gate and in this gate, but here you can see both the inputs are reaching at the same time. So, there will be no glitching power dissipation here, both the inputs are reaching here at the same time, so there is no glitching power dissipation. Similarly, these two inputs are reaching at the same time, so there will be no glitching power dissipation. So by balancing the circuit, the glitching power dissipation can be minimized. So not only you have to consider the functionality, realizing the particular function, you have to realize in a balanced manner, so that the glitching power dissipation is reduced. Then you can use different logic styles like static CMOS, with which you are familiar with, or you can use dynamic CMOS, or using past transistor logic style. I believe these logic styles have been introduced by some earlier speaker. So you can use different logic styles which will require lesser capacitance and lesser switching activity. So instead of going into the details of the logic synthesis by using dynamic CMOS or past transistor logic, I shall simply discuss about the comparison of the delay and power dissipation and the delay. You can see this is the standard static CMOS circuit, and these are the various area required, delay required for different benchmark circuits, and these are the power dissipations. So if you use dynamic CMOS circuit, the area can be reduced by 16%, delay can be reduced by 37% on the average, and power dissipation can be reduced by 25%. If you use past transistor logic circuit, the area can be reduced by 33%, the delay can be reduced by 47%, the power dissipation can be reduced by 17%. So power delay product, that is your energy required, can be roughly 50% in both the cases. So you see the benefits of this technique, the benefits of using different logic styles. I mean, these are essentially the same thing shown with the help of bar graphs. Now coming to the leakage power, as I told in the beginning, leakage power is becoming very important in the deep submicron technology. Why? It is clear from this diagram. You can see, as long as we were in the 0.35 micron technology, there was no leakage power dissipation. Leakage power dissipation was almost insignificant, but it is growing exponentially as you are going beyond 0.35 micron. You can see here at this point, that is your 90 nanometer, the dynamic power and leakage power is more or less same. That means the leakage power is roughly 50%. So we must develop technique for minimizing leakage power. So this exponential growth must stop if we want to realize a chip which will actually can be used in practice. And that is why lots of emphasis has been given for reducing the leakage power. Question is, how you can minimize the leakage power? It has been found that the leakage power has strong dependence on the threshold voltage. It has exponential dependence on the threshold voltage. As you can see in this diagram, if you increase the threshold voltage, the subthreshold leakage current reduces exponentially. This side is logarithmic, plot is logarithmic, semi-log. So this side is linear and this side is log. So leakage power reduces exponentially as you increase the threshold voltage. So by increasing the threshold voltage, the leakage power can be reduced, but unfortunately we are facing the same problem here. As you increase the threshold voltage, delay increases exponentially. So we have reached a vicious circle. Question is, we want to reduce the leakage power, but we do not want to increase the delay. So we have to develop tools and techniques which will help us to minimize leakage power, but not increase the delay. So I shall discuss some of the techniques. So what basically has to be done? We can use low threshold voltage transistors which will give you lesser delay but higher leakage current. We can use high threshold voltage transistors which will have larger delay but lesser leakage current, and this is the range over which the threshold voltage can be used. So, this is the low threshold voltage and this is the high threshold voltage. And question is how you can really change the threshold voltage of a transistor in a circuit. How can you do that? There are several techniques. One is you can use multiple channel doping, you can use multiple oxide thickness, you can use multiple channel length, or you can use multiple body bias. So, these are the techniques that can be used to control the threshold voltage, and then the different techniques that can be used as shown here. One is variable threshold voltage CMOS, VT CMOS approach. Second is multi threshold voltage CMOS, empty CMOS approach. Last one is dual VT assignment approach. So, I shall very briefly discuss about these three techniques. This is the traditional CMOS transistor. Here you see the source is connected to the substrate and which is connected to the ground. Here the drain of the PMOS transistor is connected to the PUL and connected to the supply voltage VDD. But now what you have to do, you have to disconnect this. Substrate has to be separate and PUL has to be separate, and if you can do that, then this is the structure that we can have. These are the substrates to which you can apply different different voltages. So, when the circuit is operating in normal mode, the substrate of the, that means the PUN well is given a voltage of 2 volt. Then the threshold voltage is 0.2 in the active mode. So, you get high performance. Then when we go to standby mode, you apply a a voltage of 4 volt to the substrate, and the threshold voltage increases to from 0.2 to 0.6, and as a consequence